the key thing that one needs to prove is really well-definedness. Okay, the key point here is that this definition is well defined, and why does one need to worry about that? Because we are picking representatives from these classes W1 and W2. So it's not a priori clear that suppose I changed my representative. So here's what we will need to show. What if I pick different representatives? So if x1 is another representative, it belongs to this equivalence class, okay, and I pick a different representative x2 from the equivalence class W2, okay, then so what does that mean? I.e., I have, instead of taking W1 as my representative, I am thinking of x1 as my representative of that class, and similarly, okay, so I'm changing my representative. Then, so suppose I do this, then I need to show that my right hand side will be the same answer, whether I do W1 star W2 and take the concatenation, or I take x1 star x2 and take their concatenation, the answers should be the same. So okay, then we must show that x1 star x2, the equivalence class, is the same answer as what you would get if you took W1 star W2. Okay, so this is what showing well-definedness means. Okay, so let's prove this. Again, it comes about from the special way in which the equivalence class or the equivalence relation was defined. So observe, what are we given? We are given that x1 and w1 are equivalent to each other. So let's prove this. Given, what's given is the following. These two are equivalent, and what we need to prove is that the concatenations are equivalent. x1 star x2 is equivalent to w1 star w2. Okay. So what does equivalent mean? It means there is a chain starting with W1 ending at x1, in which each intermediate step is obtained from the preceding one by an application of a basic rewriting rule. Okay. So let's write that down. So step 1, I start at W1, okay, and I use my basic rewriting rule. I get some word. I use again one of the other rules, it becomes some other word, etc., till I finally am able to reach x1. Okay, this is what it means to say W1 and x1 are equivalent to each other. Okay, similarly, I have W2 and x2. So I can start at W2, I can follow my rules successively till I reach, well, okay, so that's what the definition says. Now, given this, we need to show that if I start with W1 star W2, I can reach x1 star x2 by means of my basic rewriting rules. Okay, now the way we do this is just via this simple observation that look at this initial chain starting from W1 and going to x1. What does a basic rewriting rule do? The basic rewriting rule has the following form. So for instance, if this is my word W1, I look through the letters in W1, I either find a successive pair of the form AA prime, etc., which I delete, or I take my word W1, I look through the letters, I pick some position, and there I insert a pair AA prime. Okay, so the transformation that I perform has this very specific form. You either collapse or you sort of expand at a certain location in the word. So if I go from, let's look at the very first step of the chain, I go from W1 to whatever is the next word in the sequence by means of some basic rewriting rule, then here's what it means. It means that look at W1 and the next guy. Now to W1 on the right hand side, I can let me try doing this. Let me concatenate W1 on the right hand side with the word W2. Okay, and the next step in the chain, I'll do the same thing to it. I concatenate W2 to that word. Now, if this second guy can be obtained from the first one by some basic rewriting rule, then it follows that W1 star W2 will lead to that word star W2. Okay, I can take the second guy and I do W2 to it. So maybe I should give this a name. So this intermediate step, suppose I call it Z1, that's my word. Then here's what I mean, that if from W1 to Z1 I can go by means of a basic rewriting rule, I can also go from W1 star W2 to Z1 star W2 by the same rule really, okay, because I only need to apply that rule to the W1 portion of my word. Now and so on. So the next step again, because I can go from Z1 to the next fellow Z2 by means of some rule, it means I can also go from Z1 star W2 to Z2 star W2 by using the same rule but only applying it to the Z1 portion, and so on. Okay, so keep doing this till you reach the end. So the end here is X1, but of course remember I have starred every one of them with a W2. Okay, so I've started at W1 star W2, which is what I need to start with. Okay, so we have managed to go from W1 star W2, which is what we wanted, but we have only reached X1 star W2. Okay, but that's already a very good start, because now we do the same thing with the other sequence. We know that we can start at W2 and reach X1. So now let's do the same thing here. This implies now I will sort of concatenate on the left of W2. So starting at W2, I can reach the next step, whatever this word is. So let's call this Z1 dash. Now what I do is to concatenate X1 on the left of W2, and because I can go from W2 to Z1 dash, it also implies that I can go from X1 star W2 to X1 star Z1 dash in the same manner, and by the same logic as before. So I keep applying it to the next step of the chain and so on. So I keep doing this till I reach the very last step, and the last step is X2 but concatenated on the left by X1. Okay, so what this means is if I start at X1 star W2 by applying left concatenation to the second chain, I can reach X1 star X2. Okay, so now I just put these together. So what have I managed to do? I have managed to start at W1 star W2. I am following this chain of rewriting rules. So at this point, this and this are the same. Now I follow after that this chain of rules, and finally I reach my destination. Okay, so what this means is that W1 star W2 is in fact equivalent to X1 star X2. Okay, as required. So what this means is that my on my group G, or at the moment my set G, the binary operation that I have defined is, at least it makes sense, it's well defined. Okay, but we called it G for a reason. We are going to make this into a group. We are going to show that it actually becomes a group under this operation, and that's really our in some sense our main theorem. That's going to be the free group. So G is a group under the binary operation that we just defined. Okay, proof. Well, what all do we need to show? We need to show that the binary operation is associative. Okay, why is it associative? So we'll show that first. Observe the definition said if I take W1 multiplied by W2. Okay, let's just write out the definition of associativity here. This by definition is W1 star W2, the equivalence class of the concatenation, multiplied by the equivalence class of W3. Okay, which by definition again is the equivalence class of W1 star W2 star W3. Okay. But observe that what's inside the representative of the class that I get here is just the concatenation of these three guys, W1, W2 and W3, and the concatenation operation is of course associative. So I can replace this triple with say W1 star W2 W3, and that by the definition of the multiplication in G will just become this product, okay, and that's exactly the verification of associativity. Okay, now the identity is also easy. So there is an identity element. What should the identity element be? Well, so let's call it E, maybe the identity element of this group G. Well, I claim it's nothing but you take the equivalence class of the empty word. Okay, so that is the empty word in words of S hat. The equivalence class of the empty word, by the way, is it has lots and lots of words, remember, right? So we looked at A, for example, A prime, A prime A, those basic rewriting guys, they are all in fact in the equivalence class of the empty word. So this is in fact the set of all words which, if you keep applying rewriting rules, will finally come down to the empty word. The claim is that that serves as an identity, again by definition, because the multiplication just says for any word E, if I multiply it with the equivalence class of the empty word, I just have to concatenate W with the empty word, but that's just W. Okay, and observe the same logic holds in the other order. If I hit the equivalence class of the empty word with W on the right, then of course it gives me W. Okay. So in some sense, these two properties just follow from the corresponding properties of the star operation. So no surprises so far, but the reason we were doing all this is because the star doesn't admit inverses. Okay, but the important property here is that this does have inverses. Okay, in other words, it's a group. So let's verify this. Let's check that given any element of G, I can construct an inverse of that element with respect to this new operation that I have defined. So for a start, let's just look at the two basic generators A and B, the alphabets. If I just take the single, if I take the equivalence class of the word A, the question is, what is the inverse of this guy? So in other words, what equivalence class will you take such that, what should I put here, so that this product gives me the identity element? And remember, the identity element just means it's the equivalence class of the empty word. Okay, and observe that, well, by definition, we already know something. So let's just throw that in. Let's perform a simple computation here. So observe, if I take A and I multiply it with the equivalence class of the element A prime, then by definition this is the equivalence class of the concatenation, the word A with A prime, which again by definition is just A prime, the word of length 2. But remember, A prime by the rewriting rule is the same as the empty word. Okay, so in other words, it says that A equivalence class multiplied by the equivalence class of A prime is in fact the identity element of this group. Okay, and of course in the other order as well, A prime multiplied by A would also give you identity. You can also check that the same is true of B and B prime. So this is what I meant when I said in the beginning that A prime and B prime will eventually perform the roles of the inverses. Okay, that's only, we have only constructed inverses for these special one letter words, if you wish. What about a general word? That's also very easy. So let's just do it by example, and you'll see the general picture very quickly. Suppose I take the word W equals A B B A, for example. Okay, so the question is, what should the inverse? So maybe I should make it slightly asymmetric. So let me put two A's on the end. So A B B A A, for example. Okay, so take this word W. I want to know what is the inverse of this this word. Okay, so I claim here's a simple prescription. You just look at this string of letters, you read them in reverse. Okay, and when you read them in reverse, you just change all the A's to A primes and B's to B primes. So here's the prescription, the inverse of W. So let me call it W bar for now. This is just read W in reverse and replace any symbol that you see by its dash. Okay, so maybe I should call it replace each letter by its dash. Okay, so in other words, here I apply this prescription. I read this in reverse and I see two A's from the end, so I make them dashes. I make B's into dashes. So here's my claim is that this new word will serve as the inverse. So let us check. So how should we check? By definition, this product is just W concatenated with this new word, A prime, B prime, B prime, A prime, which as we know is A, B, B, A prime, B prime, B prime, A prime. So here's some long word, but I claim that if I keep applying my rewriting rules successively, I can convert this word into the empty word. Okay, so let's just do this sort of right there. So let me write down this word and I'll convert it into the empty word. So A, B, B, A dash, B dash, B dash, A dash. Okay, so let's just do it right there. So I have this pair A and A prime right over here. So I know that pair can be erased. I can make it into the identity, into the empty word. So I erase that from my word. Okay, now I look at what's left. Now again, in what's left, I see that an A and an A dash are paired up. So I can erase them. Okay, now I look at what's left. I see that this B and this B dash are paired up. So I erase them. Again, what's left? The B and this B dash are paired up. This A and this A dash are paired up. Okay, so you see that's exactly how we constructed the inverse. We just read the word in reverse, and for every symbol we just took its dash. Okay, and the reason for doing this is because exactly this sort of pairwise cancellation is going to happen. Okay, and in fact this was just a particular example, but more generally the word can have dashes as well. Okay, so here's here's another example. So if I have A, B, A dash, A for example, then I claim that the inverse of that equivalence class is just read the same thing in reverse but put dashes. If you see A, put an A dash. If you see an A dash, you convert that to an A. So that's it's in some sense A dash dash is like an A. So I claim it's this element. Okay, and I leave this for you to check. Okay, and it's easy to write a general prescription as well if you wish, that if W is a word which looks like x1, x2, xk, each xi is a letter, it's either A, B, A dash or B dash, then the inverse of W is just given by the equivalence class of, well, read it in reverse, so yk, and I change all the x's to y's, where what is yi is just the dash of xi. Okay, so I'm just being a bit loose here, but you know what I mean. Each xi, if it's an A, then yi is A dash. If it's A dash, then it is an A. Okay, so what have we done? We have therefore proved that this group, so finally we have managed to do what we set out to do. We have constructed a group G with respect to this binary operation. So G with respect to this binary operation is called, so its definition, this is called the free group on the two symbols A and B. Okay, so observe it is it certainly contains in some sense the elements A and B, and next time we'll start looking at some of its other properties. Okay, for now at least the motivation for this terminology, I mean it's not yet fully clear, but we at least said let's start with A and B, let's not put any relations, just sort of let A and B be arbitrary symbols, let them generate, look at all possible products and so on. And in some sense what we did by this enlargement procedure is to say let's not just take products of A's and B's, let's sort of also take their inverses, let's also throw in two formal symbols which are like the inverses of A and B, and sort of take all possible products, all words with A in which A's, B's, A inverses and B inverses occur. Okay, and in some sense that's really what the free group is capturing. Okay, so more on this next time.